All right, so there's our opening slide. And so that from that long title, we're going to try and break this down into a high level understanding of digital engineering and what that includes. And so we'll go ahead and get started. Next slide. So first couple of slides, I'll talk first about very quickly give you a background for myself, and then we'll do the same. But I've been in the NavAir organization, as you can see, for almost 40 years, long time. And so I have a real attachment to the Navy and the air part of the Navy and the weapons systems, and trying to make those successful has always been a passion for me, and it continues to be. I started off working in our instrumentation ranges. It's on the left side of the screen there. I worked on the Tomahawk program for some time, and then formed what we call the Performance Resource Team. That's essentially the name of an organization that we've had on across the NavAir organization for over 20 years. And so it's successful in terms of just existing, but also working with teams all across the NavAir organization. And you see that map of the United States that outline NavAir are these major sites. I'm on the West Coast at China Lake. Point Mugu is our connected organization. Together, we are the weapons division. So we make all the weapons systems and then integrate those with the platforms like the fixed wing and rotary wing, in other words, airplanes and helicopters. And at Pax River, out on the East Coast side, you see Pax River and Lakehurst. And between those two sites, they're the aircraft division, and they're the ones that certify those platforms that we integrate the weapon systems for. Together, we present the warfighters with successful, capable systems that they can go out on a mission, be successful, and get home safely. That's what this is all about. Other organizations you see on the map are support organizations, like where we take airplanes and we refurbish them at North Island and Cherry Point and Jacksonville. So anyway, just a real quick overview, but currently I am totally involved in, and have been for 4 years, in the acceleration of systems engineering development. That's led me to get more involved with the digital engineering side of things, and hence the reason I'm going to talk to you today, along with Will, about what that encompasses. So that's not only about me, but what leads you to all of this. So Will, go ahead and tell us about you.
All right. Yeah, Julia did a great job giving the bio, so I'll make this quick. I got my mechanical engineering degree first, and did some small software hardware projects using my mechanical engineering degree in the DoD space. And then I went down, worked for NAVSEA, got some testing experience, and got my master's in systems engineering, where I learned the model-based systems engineering and Cameo stuff that we will touch on today. I then switched over from government side to the contractor side, worked for L3 Harris, worked on several different projects, led the FVR, which is this system here. It has a vertical takeoff and lift, and then it does surveillance missions. Very cool project. And then I transitioned to Raytheon, where I worked several different subsystem projects for satellites and advanced fighters. So that's what I'm doing now. I work in Cameo and contract with internally different Raytheon projects every day. So this has been a fun journey that I've had, and yeah, I'm excited to talk about it.
All right, so here's our agenda. We're going to touch on all of these things. I will start out with a system engineering, digital engineering bottom line, kind of a where we're at. So really the first half of this, I'll do a few slides, and I'm going to cover what from a DoD and Navy perspective, what this means, and how we're going to take it forward. And then the great thing about this is connecting with Will. He's got experience at the detailed level of implementing this stuff. So it'll be great. I think a good combination of what it is and how it's done. And then we will plan to take all of your questions and deal with those at the end of the presentation. We'd like to go ahead and go through the slides and major points. So please put your comments and your questions out in the chat, and then of course ask questions at the end. We'll be looking forward to that. So let's go ahead and get into this. So next slide. So as I said, these are the key points of what we've been doing to make systems engineering accelerate over these last few years, as we've realized in the NavAir community, and I think we see this throughout the government and even many major contractors that are out there in the private industry world. We are having a wisdom gap that we are seeing the need to do something about it and not let it passively continue. And what we mean by that is folks are leaving with knowledge faster than we are able to replace them. So a big part of system engineering is accelerating, making it happen. And then what we see with digital engineering is this has become a very key part of what we need to look forward to as part of accelerating that systems engineering capability, at least for ourselves in NavAir, to make sure we're delivering those quality products on custom schedule. So let's go ahead and get into some of the high level details of what digital engineering is and how it fits with systems engineering on the next slide. And so to do that, I put together this view of digital engineering and what it truly is. So it's kind of a one slide history fun thing that I've created. So understand, digital engineering is really a set of methods and tools that amplify the power of systems engineering. So bottom line, systems engineering, as it shows in the top box, will always require engineers, engineering judgment, and they will perform these types of things, from trade studies all the way down through the list to logistics and beyond. Go out to the bodies of knowledge for systems engineering, and lots of good information out there. The government has stopped trying to define their own definition and has connected with that, and so I will reference some of that as we go into this. But when you look at systems engineering and where the history of it, and I'm starting the history here from probably the previous century, the beginning of that century, and look at the idea of 2001: A Space Odyssey and the apes looking up. In caves, engineers used pencils and paper and drafting tables, slide rules, all these kinds of things that, boy, we couldn't imagine today just being restricted to that. But through a few decades of evolving methods, they'd create, deliver, maintain systems. And, think of, from my DoD perspective, and especially Navy, but, airplanes and weapon systems in World War I and World War II to, defend our freedom, to make the world better, and all of the other things that have happened. That's what we started as. Caves got furnished with computers, and that started to give engineers this capability. So by the 60s and 70s, computers became something that were really helping things happen. By the early 80s, of course, we had personal computers, we had calculators by then, all of these tools that you see in the box in the second column there at the bottom. And that helped, along with a few standards, to write, update, and execute system of systems. So, now we were looking at how do the weapons go onto the platforms, onto the airplanes. from a Navy perspective, a NavAir perspective. And I'm sure you can see that in many other areas if you think about where you work and the kinds of things you've been involved with. But next that happened in the late 20th century as we get our caves furnished with networks. Now we started to connect through World Wide Web and other kinds of networks. And eventually with protocol, we were able to share, operate, and deliver all of the kinds of things that make up these systems of systems, but in a more virtual way. And we certainly learned in the last couple of years with the pandemic we've all gone through, how much we can truly hang on a network and make happen to get that virtual accomplishment of delivering products and services to our customers. In my case, it's the warfighter. In many other industries, it's whatever applies and makes sense there. What we're starting to see now, we've seen for the last, I've been involved in looking at digital engineering for about 4 years, but it's been an up and coming thing that's happening, is the idea of sharing the engineering in a way that allows for quick decisions. And so where we are in the late 20-teens and 2020s now, where we're looking at how we share models in different fashions or from different disciplines, mechanical and electrical, software, et cetera, et cetera. So all of those things allow us to do things like digital twins, but that leads to authoritative source of truth being in place and strong, heavy networks that can support this virtual world that we see the need for, and it will happen. It is happening. We have tools and languages, and we will talk more about that in detail as we get into second half of our brief. But bottom line is we've come a long way, and we've got a long way to go with how we're going to do digital engineering. So the question becomes, so what is digital engineering? It's making models. Well, we've always made models. Well, there's something much different about what models are here in this regard, and we'll talk about that as well. So let's go to the next slide. So again, from my perspective, Department of Defense and the U.S. Navy, what happened in 2018 for DoD was that a strategy was put out of what are the 5 goals of this thing called digital engineering, and this document, it's on the footnote of the slide. I see it's cut off at the bottom, but that's a document that you can look at and see and find out what these 5 goals. The Navy then took that 2 years later into their objectified version of those goals, and they map very much one-to-one. And it's these 5 goal areas. This is quite an eye chart, but the idea is achieving the top level goal, number 1 goal, having wide and deep models of the systems that we have and being able to make quick decisions. Those are the details that are in goal number 1. But in order to make that happen, we have to climb from the bottom up. And we start with goal 5, objective 5, change the culture and get our workforce to understand, adopt, and use this as part of what the process and the methods for making the products that they have to deliver and pull together. So that's where things like model-based systems engineering and a digital engineering workforce come into play. However, that requires objective 4 having a digital backbone that's very high capability, tons and tons of data to make quick decisions and to see how changes in systems of system parts and pieces affect others. That includes at level 3 or objective 3, having methods that fit into the processes we use today for how we're developing software intensive systems that incorporate everything from the weapons to the platforms and everything in between, the maintenance of those systems and so forth. So to truly achieve what digital engineering specifies, you then have to reach this number 2 goal level, which is providing an authoritative source of truth or knowledge. So getting to the point of not redesigning each time a major program has to use the same components, but rather having one identifiable and subscribable version of that requires a lot of change in culture that we talked about at 5 in order to make that happen. When that happens and we subscribe to each other's high-level designs to drive the systems, this means that we will be able to then achieve what we started out at the beginning of this slide, formalizing the development, integration, and use of models wide and deep. So that's a real fast run through. So we'll go into a little more of this. Let's go to the next slide and look at the where does this idea of systems engineering come from, and what's the need for digital engineering to make it happen. So if we start at the basic fundamental role, engineers devise and deliver systems solutions, to various problems, challenges, requirements from the sponsor, from the end user that says, make this work, build me one of these, create this function, capability, etc. Well, specialized actors and roles, when we have teams of folks working together, we have systems engineers that help lead a program and coordinate its efforts and pull together, the performance and the products and services of each individual member of a team in that role to address those challenges that come together to develop a system, and eventually all the systems that make up system of systems, like we talked about earlier. So where the rub comes in these days, and it's actually been around for a while, is the systems are getting very complex and very large, and in fact, huge. So the purple words are essentially saying that we need to become more capable of pulling together all kinds of potential solutions. Leads to confusion. Sometimes we've had problems where we'll be in a battle, for instance, in the past, and airplanes can't talk to airplanes because they've designed at the highest levels the same systems in different ways. So this is a reason that has driven why we need to go to having a digital engineering approach that takes the authoritative source of truth that we talked about as a fundamental key part of this to make that happen so that we can connect and communicate and be successful. So digital engineering on the right, again, is what integrates all of these computational-based approaches, pulls them together in a way that we can identify quickly when something affects design in one subsystem with another. Getting through the noise in the middle, it really leads down to that entry-level model-based systems engineering. This is something that gives us some capable building blocks at the start so that our lowest working level engineers in teams on projects and programs can start to build this capability with this new way of viewing the idea that we all share in the designs that drive everything else in the development cycle. So what we've added on the right, Will's going to talk to this, is how do we use in a digital engineering format, the tags and use the model then to complete the systems engineering V that we're all very familiar with. So reference here, you can see this one on the bottom here, United States Navy and Marine Corps transformation strategy. That's the basis that we pulled this from to just talk about how we progress from the system engineers' need to do digital engineering to be really successful in the future with such complex systems. Next slide, please. So the digital engineering documentation that we're referring to, this one comes from a measurement framework that really lays this out very nicely in these core concepts. There's 3 core concepts that define really how digital engineering happens, and it starts with an authoritative source of truth. So we've talked about that. That was objective 2, and the definition or objectified it as the second objective in digital engineering. And Will's going to get into some more details on these, but in the second component, model elements. So these are abstractions, different components, parts and pieces, different angles and views of the system. What you'll hear him talk about is the fact that you can't see an entire system modeled. You can see views and different parts and pieces of it in any one moment. It takes bringing all of these views together, and he'll do the job of showing that at the next level down. Finally, life cycle phases. So this is where we need to have the idea of a methodology for how we do MBSE, model-based systems engineering, incorporated into the current processes and methods we have today for how we build these complex systems. And this is going to then accelerate and make that faster. So with this, I'm going to hand it over to Will, and he will take these core concepts and expand on them for us.
Awesome. Thank you, Jeff. Yeah, so we're going to have one slide on each of these going forward. So this next one is the first one is the authoritative source of truth. So the concept that we've been talking about, the digital transformation is going from a document-centric approach to a model-centric approach. And what that means is because systems are so complicated that you got, I don't know, 6 or 7 or 8 plus documents that are describing the system. And what happens is there's a change that occurs down the line through the life cycle of this process, and you have to go back into every single one of those documents and go back and fix that specific change, which requires a ton of time on the systems engineering team to go back and do that. And then also, if you're just trying to read a document, you got to make sure you're reading the most up-to-date document that exists. So that was the way that it was done. So a lot of rework, and you never knew if you had the latest and greatest document. And so the new way to do it is this digital way, which has an authoritative source of truth, which just means everything is connected. And so when you change something in one location, it like spiderwebs out and communicates with everything else that it's touching, and it changes that update in all of the places. So you only have one change, and then it propagates all those changes throughout the entire thing. So basically, instead of having to figure out what document you should look at, and if it's the latest and greatest, you can just refer back to the authoritative source of truth or the model, and it will tell you the latest and greatest. So the goal is to thread all the information from different disciplines together to promote communication and reduce confusion. And then the model can be fed up to leadership, which uses their management expertise to provide high-level direction. And so what we're talking about is this chart right here on the left, and how Cameo and model-based systems engineering kind of connects to that. Basically, you've got model-based systems engineering, which talks to your high-level management, so as well as down to your low-level subject matter experts that would be really good in one field. They go down really deep with their technical depth, but they don't have the breadth that like the systems engineering or the management would have. So before this model-based systems engineering, everything was kind of disjoint, and it was kind of difficult for things to be compiled and the communication was constantly a struggle. So with the modeling tools that we have now, we can communicate from subject matter to subject matter, whether that be mechanical to electrical to any sort of specific domain. And then all of these specific domains kind of tether back into the systems engineering team, which is who is responsible for these models. And then the systems engineering team sends up the high level stuff, the data, to the management so that they can make the best decisions. So moving forward to the right side of the screen, it's kind of a cartoon that explains how different SMEs or subject matter experts will have a different viewpoint of what the model is. We got a plane here, so production sees this view, Aero sees this view, and this is really how it works. And if you don't have one location to have all of your data go to, then it becomes difficult to communicate. And something that should be very, very, very simple is not realized until much later. So you can see that having all your data in one place would really help reduce risk. So moving on to core concept 2, which is the model element. So the model element, so people ask me what I do every day, and I tell them simply that I put blocks on a screen, and that each of those blocks would be an element. And you can have structural elements, you can have behavioral elements. So an element is just an entity that can connect to other entities within your model. And it will represent either a structural aspect of the model or a behavioral aspect of the model or a requirement aspect of the model. So you will obviously connect those three domains and using different dependencies. And what this is referring to is that obviously you're not going to be able to model everything that exists for a system. You have to just do a reduction and only model what's important. What you got to figure out, model with a purpose. You got to figure out where you're trying to go, and then you got to model for that. So the model elements must have the correct properties to help most efficiently solve the problem. So correct is in quotes here because you don't want to, you just want to go to the right amount of depth. So moving forward, we have the difference between a model and a diagram. So we got our dice down here, our die, and this would represent the model. But the model itself is multi-dimensional, so it's much more than just 3 dimensions. You couldn't actually see your model on a screen because it's got all these different sides to it. So what you do is you look at a view or a diagram, which is going to tell you like one side of the die. So that's kind of explaining. You can't just look at the model. You have to look at a view of the model, which is a diagram. And each diagram is supposed to have an intent. So whether that be telling you an activity flow or a structural breakdown or some sort of parametric, which would give you mathematical equations, each diagram is going to have an intent and a specific set of stakeholders that are intended to look at and interpret that diagram. So over here on the right, we have the kind of modeling environment. So Cameo, this is our software that we use typically to do model-based systems engineering, and you can connect the Cameo tool to other softwares. So if you're trying to do design, optimization, analysis, and simulation, you might want to connect to MATLAB tool or Simulink. And if you're trying to get your requirements in there, you can connect to IBM's DOORS or RecIF format. So this scales out much more than this picture is showing. But the idea here is that if something changed in Cameo, then that change would be propagated out to the other softwares. And that's what I've got down here with this Meta owns Facebook and Instagram and all that. And if you tag something in Facebook, it then sends all that information to Instagram or Messenger or whatever else. Everything is connected and seamless. And that's what we're trying to make here. So core concept number 3 is the life cycle. So what we've got here is that the system has its own life cycle. So from cradle to grave, if you're in systems engineering, you're very familiar with this V. So we decompose the system, and then we recompose it, and then we have verification, validation. And this is an iterative process. And basically, MBSE, or model-based systems engineering, makes this process much easier, and to do certain things like sensitivity studies or swap outs. It makes the systems more modular, and it disrupts major primes from taking advantage of the government. And it reduces vendor locks. So this is probably a big asterisk here for the reason why we're doing this. Basically, if we go out, or the government goes out and says, hey, I need you to build me a new airplane, and they do that, the contractor intentionally makes it difficult to integrate in for their special wing or their special propulsion system. So essentially, if the government ever wants to make upgrades on that propulsion system, they pretty much have to go back to that same contractor and say, hey, can you make upgrades to that? So then that contractor gets to write their own ticket for how much that's going to cost. So this new model-based approach puts everything in the model for you, so that it's much easier for different contractors to compete for that new propulsion system, because that new propulsion system, all that information is already in the model. So basically, that the person who made the initial airplane is no longer like light years ahead on the design phase than the other contractors. So moving forward, there are several different methodologies which explain how to create system architecture. We'll touch on the magic grid methodology very quickly, but the goal here is that basically we want to create the matrix. We want to create everything digitally, so that then we can just build on that. What we had before we went digital is everything's on paper. So anytime we want to make something new, we have to start with a blank sheet of paper or some template. But that template is very, very, very limited. Moving forward, if we've modeled everything very well, then we can go ahead and use that model to start out with. I mean, and we reuse parts all the time, and assemblies. So if we have some team that's used this assembly in multiple different places, they can then aggregate that assembly with other sub-assemblies that different teams have made to create a completely new system. And it really is, it's like we're creating the digital Legos, and then we can put the Legos together in a much simpler, faster way once everything is done. So then I'll touch on the digital transformation, the digital trinity. So the 3 parts of the trinity is the digital engineering, which we've talked about. And down here, we have some just sources to read more about that. And we have agile software and open systems architecture. So agile software is specifically talking about continuous development, where you are you're constantly getting to a point where everything works. So instead of like a waterfall approach where you've got one deliverable at the end and then you just send everything off and it only has to work once, this is kind of like an incremental thing where You're constantly improving and updating your model, and at the end of each sprint or time sequence, you will have something that works. And you can kind of look at this little diagram, the DevOps diagram, where you plan, code, build, test, then you release, then you deploy, then you operate, then you monitor, and then the whole system kind of goes over, and it just goes on forever. So we're continuously improving what we have. And so it's kind of that culture shift that Jeff was talking about earlier. The last part of the digital trinity is open systems architecture. And what this is kind of talking towards like the standards. And basically, we don't need to silo all of our resources apart from one another and have all of these models separated. And because ultimately, we want to be able to connect them very easily and use them for a bigger system, like or a system of systems. So we have several different competing standards that are kind of working with each other, working to try and figure out the best way to model systems and subsystems so that they can be integrated together at a higher level and broken apart at a lower level without breaking the model. So moving forward, this is the last slide. I'm going to try and tie it all back together of the digital trinity and where we are now. So Jeff gave a good example, high level of where we are, and I'll kind of break it into like the last 4 years. Where are we? So first we have to embrace digital engineering, which is a huge shift in culture. And then we have to select the methodology, language, and tool, and then and struggle through the standardization process. And then we'll create a good competitive solution, which is much better than the analog or the paper document-based approach. So this is step 1, this is step 2, and this is step 3. This is a like kind of a music gone digital analogy for kind of that it will explain how digital engineering will be implemented over time. So as everybody's familiar with, we had our our CDs, our records, and then we kept on getting smaller, but we were analog, and eventually we went to the iPod. And it took us a long time to give up our CDs because it seemed like just your small compact CD player was still a better alternative than having to deal with the mess of the iPod. So there was a lot of struggles over standardization for these digital formats that we had right when we went from the CDs to the digital side of the house. And it seemed like it was going to be much more of a pain than it was worth. But we kept on pushing forward, and now we have all these good solutions such as like Pandora, SiriusXM, Spotify, or iTunes, which we can all agree is better than having your CD player and carrying that along with you all the time. So where we're at right now is this step 2. We're still struggling over the standardization of how exactly we want to format everything so that we can get to this good solution down the road. So to talk to some of the standardization, I and Jeff have both said methodology, language, and tool. So I will talk through that. So MBSE, Model-Based Systems Engineering, is the addition of all these 3 things. Methodology is kind of like how you want to put things together, how you want to structure everything. And we have used the magic grid approach in most of the examples that we've shown today. And then SysML, this is the language. And then the tool is Cameo. So the tool this is the software, and then these are like the rules. So this would be like C++, and then it's just an example of another language. So all that together, that's what we're working towards to create a set of standards so that we can eventually get a good solution at the end of the day. So with that, go to our sources page, and that is it. So we made it.